So we have come to board of the course. We are at the last lecture for the first half, which is looking at closed loop control systems and looking at three different types of controllers, P, PI, PID, and what do those mean, how do you tune the controllers, and so on. In the last lecture, talked about tuning based on two distinct ideas. One is what I called as stability based tuning, where you look at how far you can push the controller in terms of the best performance and getting it to the edge of stability instability, and then the tuning rules basically back off from that point. So the Ziegler Nichols tuning table, if you look at the tuning, let's say for a P controller, you would have noticed that the gain would be kept at 0.5 times KCU. What basically that means is that if I keep the gain at KCU, the system becomes unstable, but I get the best performance. But to hedge for the fact that the model might not be correct, or I could have disturbances and so on, I pull back the value of KCU by 50%. That's the reason why I actually keep the gain as 0.5 times KCU. So that is what I mean by backing off from the most aggressive value that you could have for the control gain. And then using the same Ziegler Nichols, we saw that you could tune the PI controller, and depending on the KCU and PCU, the gain and the time constant or the integral time of the PI controller is chosen based on the table. And if you notice, for all of those, there will be some multiplication factors for this KCU and PCU and so on. Those you can basically interpret as how much you are trying to back off from the most aggressive P controller tuning. So that was the stability based tuning. I also said that the other way to do the same thing is what is called performance based tuning, and that is what we are going to see here in this lecture. However, ultimately after all of this is done, I also said that there are tables that you look at and then use those tables for fixing the values for your controller. So we know that let us say if I have a closed loop system, let us look at a closed loop system here. I have just drawn this as two loops so that we understand what we are doing here, and this will be important when we go forward in terms of more advanced concepts in control. So typically what we will do is we will have a process. As I said before, we will model it, linearize it, get a model. Okay. Now I am going to call that as G, the transfer function for the model. And the first time I am going to kind of distinguish this from GPS, which is the process transfer function. Okay. The process transfer function, in some sense you can think of this as the true process, whatever that might be, and whatever we use as a model, whether it is first principles and linearized or first principles without linearization or just testing and then building a model based on data, all of those are basically trying to approximate this process, but nonetheless they are not exactly process. So you might think of them as G model transfer function, which is supposed to be a faithful representation of the process. So you might want to think of this model as some GM plus delta GM in a very simple conceptual idea, that there is a model that I have and anything that is left over between the model and the process, let me call that as delta GM. So this is basically in some sense the uncertainty associated with our modeling, right. So this is not captured, this is unknown, and hence there is always going to be a difference between GP and GM. And then we have to kind of account for it, and there are very mathematical and very theoretical ways of accounting for it, which is the field of robust process control and so on, which we are not going to talk about here. But nonetheless it's worthwhile to start thinking about control in a slightly more sophisticated fashion at this point, because the second portion of this course is going to need this differentiation in terms of model and process to happen, because we are going to get in a closed loop diagram both a transfer function for the model and the process. Till now we have never made this differentiation, because what we assume is this model is process, right. So we base our controller based on a model, but since model is process, while we analyze how the controller will do, how the controller will work, once implemented, we again use the same transfer function, because we assume process and model are the same. However, for the first time what we are going to say is whatever we are trying to do in terms of tuning is essentially based on a model. So, we put a model transfer function in a closed loop, and then we are going to say, okay, if this model transfer function has to be controlled very well, what is the controller? Okay. And then in reality what will happen is this controller is actually implemented in a real closed loop, and that real closed loop is going to work with the real process which I am representing by GPS. Now, if it turns out that this and this are exactly the same, so whatever is the performance that you expect to get out of this exercise, you will get here if this and this are the same. However, if this is different from this and that difference is the delta GM, then this controller will still do reasonably well if this delta GM is small, but the performance that you will get from here will be different from the performance you will get in the real actual plant implementation. So, this is a reasonably simple idea, but still sometimes we kind of miss this and then say, okay, process and model, and we keep using them interchangeably. So, it is a good idea to remember this. So, ultimately what we are going to do is the following. So, we are going to say, look, we are going to design a controller based on a model, and then we are going to implement the controller, and then we are going to, if you want to realistically study the effect of what this controller will be on process, then you have to actually truly implement this and then see what happens. Simulation wise, if you want to actually design a controller based on a model and then see how it will actually do in a real situation, what you could do is you could assume this GP is GM by delta GM, and then you can take different forms for delta GM and then keep the controller same and then study this loop quite well, so that you can answer questions like, even if the process is different from the model by this delta GM and I can use different delta GMs, how well would this controller which was designed based on the model still do? Okay, so that kind of study that you can easily do. So, that is something to keep in mind. Okay. Now, at this point anyway, even when did Ziegler Nichols, we assume the model is a process, right. So, again we are going to look at the model transfer function and then see how I can tune the controller. Now, in the Ziegler Nichols tuning and stability based tuning, what we did was we chose a form for this Kc, and then we said at different values of Kc what happens to the closed loop, when is it stable, when is it unstable, and so on, and then we found the limit of stability in terms of an ultimate gain, and then we found the ultimate period, and then we were able to tune the PID controllers. However, ultimately after all this tuning, if we say what is the performance of the controller, so the performance of the controller is how well does this Y follow Y set point, right. So, this is something we have seen, which is GP, the true process, GPC divided by 1 plus GPC Y set point. So, the true behavior, right, once the controller is tuned, if I want to see, then I have to look at this transfer function, how close this transfer function is to 1, basically gives you how well the controller is going to do, because if it is 1 exactly, Y is equal to Y set point, so that means the output is exactly following the set point and so on, but in reality it is never going to be 1, but it is going to be some other transfer function. So, ultimately you have to remember that the performance of the real implementation of the real plant performance is actually dictated by this, and we never know exactly what the GP is. We have a surrogate for that GP, which is GM. So, typically what we do is we tune a controller based on GM, and all the analysis of how well the controller will do will be based on this, where we again assume GP is GM because we do not know what GP is. And here is where you could do something like GM plus delta GM and so on to see different cases, but ultimately the proof is really when this is implemented in a control system, and then you see what happens with the actual process. Okay. Nonetheless, without doing that, if really we want to say how well the controller is going to work, one transfer function we can directly look at is this GMC by 1 plus GMC, assuming GP equal to GM. Now, in Ziegler Nichols and other stability based tuning, we are not looking at this transfer function ever. Remember that we are looking at this to construct the denominator polynomial, but we are not directly specifying a performance and then constructing the controller. Rather, what we are saying is, okay, if I have a controller form, when will this system transfer function be stable? So, we are only looking at the stability aspect of this transfer function. and then we are saying okay, when it's stable Kc is this much, let me pull it back and so on, right. Instead, another way to think about the same thing is, this is what is ultimately deciding the performance in the closed loop. So, instead of doing all this complicated things where you choose a control structure and then back off and so on, why not I specify what my performance transfer function is. I directly say I desire a transfer function of this form. Now, this is what I will get from a control design, this is what I desire. If I equate both of this and then compute a controller, then once I put that controller back in, I will get my desired performance. Okay. So, instead of kind of doing this roundabout way, it seems, where I am going to choose a controller, find the limits of stability and then come back and back off and then say okay, that is heuristic and I can see how well that does by putting into this, is one way. Instead of that, you might say, look, I am going to look at something as my desired transfer function, and since this is the ultimate closed loop, when this equals to this desired transfer function, then I have got everything I want. I do not have to really worry about stability here, in the sense that I can choose a G desired which is stable, right. So, if I choose a G desired which is stable, the closed loop has to be stable, because ultimately I am already saying this y of s is G desired y set point, and this is what I am specifying. And since I am going to be smart and specify something which is stable, so I do not have to worry about stability. All I need to worry about is whether I can achieve this, and I actually know a functional form for this, which is GMC by 1 plus GMC. So, as long as I choose a controller which once substituted into this equation will give me my G desired, then I am all done. Okay. So, that is the basic idea of direct synthesis. So, I am directly synthesizing the controller with a very specific performance transfer function in mind. Okay. So, that is what this says. So, this is a very interesting and very nice, very simple idea seems like, but this idea came quite late after quite a bit of feedback control had been done, and this idea is the one that then leads on to this internal model control and many other very interesting ideas in terms of model predictive control and so on. So, this direct synthesis is a key idea. So, to summarize, since I know the closed loop transfer function form, I say look, I am not going to do a controller based on stability. What I am going to say is I directly am going to put in what the desired transfer function is. I am going to choose a desired transfer function in such a way that it is stable, because that is a smart thing to do, and then I am going to simply equate this to this and then compute the controller. So, it looks like all advantages. Of course, this is a very powerful idea, and there are lots of things about control and performance limitations in control and so on you can learn from this idea, and as we will see in the second part of the course, we are going to use this idea quite heavily. Nonetheless, there are certain disadvantages in the sense that you are going to choose a G desired and you really do not know what is the limit of your performance, at least in Ziegler-Nichols tuning, because you are pushing yourself to the limit, you know what is the best performance that you can get. Here there is a notion of what you want, which might not really be anywhere close to the best performance that you can get. So, that is one general conceptual idea that you have to keep in mind. The other idea that you have to keep in mind is that when we do the Ziegler-Nichols and so on, from whatever experiment or exercise that we do, we actually get the tuning parameters of the PID controller directly. In this case, this G desired I give, and then I compute a controller, and I am going to get a controller structure. And remember, if it is a PID controller, if it is a P controller, the controller structure is Kc. If it is a PI controller, we know the controller structure is Kc times 1 tau is, and if it is PID, I know it is Kc 1 plus 1 by tau is plus tau ds, right. So, these are the structures that are already defined, but when I put a G desired and then compute a controller, the controller need not be in any of these structures. Okay, so, they might not even be in a PID structure. So, if you are trying to tune a PID controller using this, and if the controller that comes out itself is not in the PID form, then you cannot back out what are the tuning parameters. Okay. So, that is a disadvantage, but that is largely overcome by choosing G desired in such a way that the controller turns out to be PID, or in cases where it does not turn out to be PID, there are other minor modifications you can do, such as adding a filter and so on, and still get it in a form that has a PID form and something else before and so on. So, all of that has been worked out, but I just want you to get the basic difference between the notion of Ziegler-Nichols tuning and this direct synthesis. So, now that we have said this, so let us look at how this controller structure is chosen. So, why is this G closed loop Y set point is something that we have been talking about quite a bit, and we said this closed loop GPC by 1 plus GPC. Now, we have replaced that GP by GM. So, basically this is the closed loop control loop with the model transfer function, and as I said before, I am going to stipulate whatever is the desired transfer function I have. So, G desired, what I am looking for. So, this is something that I have to specify, because this is a performance metric that I am specifying for this controller, and once I have this performance metric, then if I want to get this performance metric, this has to be equal to this. So, that is this equation here, GMC divided by 1 plus GMC is G desired. So, if you do some very simple manipulations, let us do that. So, this is G desired times 1 plus GMC, GMC equal to GMC. Then what we need is, we need all the controller terms to one side, right. So, basically what we are going to do is we are going to have G desired plus G desired GMC equal to GMC, right. So, this is just expanding this. So, I take this to the other side, I take this as G desired is C times GM 1 minus G desired is what you will get by taking this to this side and then collecting terms. Then this will give me C equal to G desired divided by GM times 1 minus G desired, which is what I have here. So, very, very simple manipulation that we do here. Now, this is the controller structure, and the controller structure depends on whatever I have chosen as the desired transfer function and whatever is the model, right. So, remember, this has no PID notion yet. Okay. So, if it turns out that the derived controller is in the PID form, then the tuning is complete. Why is the tuning complete? Because if I get CS is some form here which is PID form, then I can write it in this Kc 1 plus 1 over tau is plus tau ds, and then once I write these numbers, I can simply read off as coefficients of the polynomial. So, tuning is already done. So, that is the beauty of this, if this turns out to be in the PID form. So, let us take one example to understand how all of this works. So, let us consider the transfer function model which is of this form, and now I have to do a tuning for this. So, I know again that my closed loop is going to be GMC divided by 1 plus GMC. So, this is going to be G desired, and now I have to choose G desired here. So, here in this case, let us assume that I chose a G desired of this form. The reason why I choose this is because this will help me cancel certain terms and get it in the PID form, and this is where the challenge lies. How do you choose a G desired which is better than the open loop while still giving you a PID form whenever you do this computation. Okay. Again, as I mentioned before, when we talked about Ziegler-Nichols tuning and so on, this will give you an idea of how you understand these two tuning approaches and how you derive insights and a lot more understanding based on this. Nonetheless, ultimately when you are actually going to implement this, again there are tables for IMC tuning, there are tables for stability based tuning, different types of tuning such as Cohen-Kuhn and so on, that you can directly read off. Okay. So, that is not really the problem here. The problem is you could read off, but what is the underlying fundamental basis for this is what we are trying to teach here. Okay. Again, so now that I have G desired, now I know the C from the last slide, I know it takes the form G desired, I think divided by GM times 1 minus G desired. So, this is a form. So, this is G desired, this is GM, and this is 1 minus G desired. Now, if you do simple algebra and then write it in this form, you will get this C to be this form. So, this looks like little strange form right here. So, what we can do here is the following. We can write this in a PID form, because the first term, this term will give you, this by this will give you the integral term, this by this, because S and S will get cancelled, will give you the proportional term, and this by this, because I will have an S here, will give me the derivative term. So, this is what we can do. Now, when you put all of this together and then slightly rewrite it in the PID form, you will get this. So, let us just look at how this works out. So, I said this divided by this will give you the Kc. So, you see 7 by 9 gives you Kc. Okay. Then I said this divided by this will give you the I term. However, so this looks like 1 over 9s because since we are taking the 1 over 9 out, this will become 1 over 7. So, 7 and 7 gets cancelled, you will get 1 over 9 times s, which is what this term will be. And then you have this term which will give you 10 over 9 times s, because again we are taking 7 over 9, you will get 10 over 7, because 10 over 7 times 7 over 9, 7 and 7 will get cancelled, you will get the 10 over 9 term. Okay. So, this is how this whole thing works here. So, now when you look at this expression, now you will notice that this is of the form Kc 1 plus 1 over tau is plus tau ds. So, that is the form that you have. So, if you read off, Kc is 7 by 9, okay. 1 over tau I is 1 over 7. So, tau I is 7 and tau d s is 10 over 7 by s. So, tau d is 10 over 7. So, this is what I mentioned in the last slide, where I said once you are able to choose a G desired in such a way that the controller ultimately comes out in the PID form, then it is easy to simply read off these numbers and those become the tuning parameters of my PID controller. So, look how easy and beautifully this tunes the controller, but the trick is in actually choosing the G desired. The key advantages of this direct synthesis approach is actually you are specifying the performance directly yourself. So, you know what you are going to get if the process and model are going to be very similar. So, that is one good thing. And more importantly, when we start the next portion of this course, we are going to see that we can really understand what limits the controller performance when I have a process, right. So, what are the components of the process which I have to take special care of, and what are the components of the process which will allow me get good control, and what are the components of the process which will inhibit or prohibit great control and so on. It is something that you can easily understand from this very simple idea of direct synthesis. This will then form the basis for understanding what are inverse response systems, how do you control these inverse response systems, and time delay systems, how do you control them, unstable systems, how do you control them, and so on. So, all of that you can actually very nicely understand from this notion of direct synthesis. As I said before, ultimately you will see tables for direct synthesis which will also be called as IMC tables, which we will IMC idea I will talk about later, but I will tell you how the tables are generally going to look. So, if you are going to look based on this direct synthesis approach, there is one thing which is the process model. So, once you have a given process model, in Ziegler Nichols you never saw a process model, right. So, everything about the process model is somehow encapsulated in the ultimate gain and the period, because the whole tuning table was going to use only the ultimate gain and the ultimate period, and depending on what the process is, the ultimate gain and ultimate period will change. That is how we bring in the process specificity into the Ziegler Nichols or the other kinds of tuning tables, whereas here we will actually get the process transfer function itself here. So, for example, let us say if this is Kp over tau s plus 1, and then because this is based on direct synthesis, you also have to give a G desired. Okay. So, let us say the G desired in this case, let us say is 1 over lambda s plus 1, then you could have the P controller term, the Pi term, the PID term, and so on. So, P controller term will be Kc, this will be tau I, and this will be tau d, and in this case if I have this, then the P term is going to be a function of this Kp, tau and lambda. The lambda will also come in because lambda is the desired transfer function. So, this is going to be tau p by Kp lambda. So, this could be one table that you have, and this tau I could be tau p itself and something like this here. Okay, so this is one possible tuning table. Now the way you read this is, supposing the process transfer function is this for you, Kp over tau Ps plus 1, and the G desired that you want is 1 over lambda S plus 1, then you have to tune, if you want to tune a PID controller, then you have to have this Kc as tau P over Kp lambda and the tau I as tau P. So that is what this says. Now if let us say you do a second order transfer function, tau 1 S plus 1 and tau 2 S plus 1. So if this is your second order transfer function, and then let us say your G desired is still the same, in this case this could be tau 1 plus tau 2 divided by Kp lambda, and this could be simply tau 1 plus tau 2, this could be tau 1 tau 2 divided by tau 1 plus tau 2, right. So now the way that you interpret this is, if your transfer function turns out to be this and you want this desired transfer function, then if you are going to tune a PID controller, you should have tau 1 plus tau 2 by Kp lambda as the P term, tau 1 plus tau 2 as the Pi term or I term, and this as the D term, tau D, tau 1 tau 2 divided by tau 1 plus tau 2. Now other than this, you will also notice in this that there is also another thing which they will call as some filter tau F, also in some cases will be filled up here. So the idea here is, in many cases when you do this G desired, you will not directly get a PID form. What you will get is based on this G desired tuning, if you get a C, and if the C is of the form Kc 1 plus 1 over tau Is, the reason why I keep writing this is I want you to get comfortable with this form so that you do not have to commit this to memory. Then everything is fine, you got these coefficients and you do whatever you want to do. However, there are cases where, so if I call this as a CPID structure, the controller that comes out of the direct synthesis after you give a desired transfer function, in some cases might have not only a PID structure, because remember this we are computing it as based on the G desired. So there is no reason why they should fall into the PID structure. By choosing G desired, we are forcing this to fall into the PID structure. So that is something that you want to keep in mind. In some cases it will still not happen, so it might be, let us say of a form of a PID which you can separate out, but then there might be something else, and in many cases this CF might turn out to be of this form, tau F S plus 1. Okay. So your controller is not only a PID controller, in the front there is another transfer function which is called the filter transfer function, which is basically another first order process that is appended to the PID controller. So that means this tau F has to be figured out. So there are cases where you will see also tau F, but tau F again will be a function of whatever parameters you use in your G desired and whatever are your process parameters. So as long as you look at these two columns of these tables, and you are able to simply compute Pi at Kc tau I tau D based on the parameter values here, and in cases where this is also filled up, then you know that your controller is of this form, and this tau F also will be computed as a function of these parameters. Now you do not have to panic that, oh, suddenly I have a PID controller, what happens? Nothing happens, because remember the closed loop transfer function is basically for us again GMC by 1 plus GMC, whether the C is CPID or whether the C is CF times CPID does not really matter, because once I put any controller here, then if I want to analyze this, I am going to simply do this as a numerator by denominator, and I have already shown you many times how you analyze transfer functions of numerator by denominator. So really this adds only another wrinkle in terms of more terms, but conceptually nothing changes at all. So it is important to remember that the fundamentals are basically how you analyze the transfer function, and that remains the same. Once you have these transfer function forms, whatever C is given, you simply put that in and then you will be able to analyze this. Okay. So with this I end the first half of the course. Just a quick recap. We started with what is the notion of control, Then we talked about what are the notions of open loop and closed loop control, and we talked about why we need closed loop control. We talked about servo control and regulatory control or disturbance rejection control. And then we said for doing control you need models. We first looked at physical systems and how you model them. Then we talked about models as being comprised of conservation equations and constitutive relationships. We took certain examples to show how to write these models. Now the conservation equations can be mass conservation, energy conservation, momentum conservation and so on, and the constitutive relationships are things that have been studied and derived from data from large number of observations. And once you have these model equations, we got to what is called a state space form of these model equations, where I have states which are differential states as far as this course is concerned on the left hand side. So I get equations of the form dx1 by dt equal to f of function of states and some inputs, and dx2 by dt function of states and inputs. Then we showed how you can linearize these state space equations to get linear state space equations, and then from there we moved on to this notion of single input single output control, where we said we are interested in one output and controlling that one output with one input. At that point I described how you think about these variables as either input or manipulated variable, disturbance variable, exogenous variables and so on. So all the terminology I described, and then I said what is a disturbance variable and what is a manipulated variable. All of that to some extent depends on the design that you have. So if you have a particular line where you put in a valve, flow in could become a manipulated variable. But if you had a valve but you did not manipulate at all, left it at only one position, then it can actually be a disturbance variable. So it is important to understand conceptually what these mean, so that when you look at the design you are able to see where I can manipulate the variables, where I have to treat variables as disturbance variables and so on. And I also said when you think about state space models, you could have multiple states but you can still look at single input single output control systems. Anyway, after that we solved these state space models in time domain, and then showed that the output will be in what is called a convolution form or a convolution integral. And then we also took the same state space equations and then multiplied this e power minus st and showed you Laplace transform and showed you how the differential equation state space models get converted into algebraic equations. And once we have these algebraic equations in Laplace domain, we showed how the convolution solution in time domain becomes simply a multiplication solution in Laplace domain. So once we have that, then we said okay, you might get the output in the Laplace domain, but really ultimately for you to understand all of this you need to get the output in the time domain. So we said the process is you have a time profile for the input, you convert that to Laplace transform, multiply it by a process a transfer function, get the output, and then you do the inverse Laplace transform. And when you do the inverse Laplace transform, I said the most important idea is this partial fraction idea. You can do Laplace transform of any inverse of any function which is of form a numerator polynomial by denominator polynomial. From then on we understood how this inversion is done, and there are only a couple of rows in the Laplace table that we use to do these inversions. And once we did these inversions, then I said any transfer function which is ns over ds form follows the same procedure. There is nothing special anymore. Then we asked the question, if I have an ns over ds transfer function, how do I figure out if transfer function is stable and so on. And then we said if the denominator polynomial is in a root resolve form, then basically look at the roots of the denominator polynomial, which could be real or complex, and as long as all the roots are strictly in left half plane, then we can say the system is what we called as stable or bounded input bounded output stable, which basically means whenever I give a bounded input, the output will always be bounded if all the poles are strictly in the left half plane. So this is as far as the open loop system is concerned. Then we said okay, that is the first time where we started by saying a control needs model. Now the model has been described, model has been solved, model has been analyzed. So how do I do this? Closed loop control. So I talked about the notion of feeding back the error and the controller taking in the error as the input and then giving the manipulated variable as the output. That way we were able to close the loop, and then I showed you in an open loop the inputs are U of s and D of s and y is the output. But once you close the loop, U of s is not an input anymore because it is going to be manipulated, and then the values for that is going to be decided by the controller. But the controller is really in some sense driven or manipulated by the set point that we give. So the inputs in the open loop, which are Us and Ds, now gets transformed into y set point s and Ds. Okay. And then in the open loop we have a transfer function between Ys and Us, Ys and Ds, and then you can add them to get the overall effect on y because of the linearity property. The same thing translates to closed loop. You have an y and you have a term corresponding to YSP set point and a term corresponding to disturbance. Okay. Now I said once I show you how to get these transfer functions, then the analysis is straightforward because we are going to use the same ns over ds form and do whatever we did for closed loop open loop systems, the same thing that we are going to do for the closed loop systems. So that is what we understood at that point. And then we said, okay, when we talk about this control, what is the structure of the controller? Then I introduced the notion of PID control. P controller is a proportional controller where you are saying my input or the changes to the manipulated variable that I am going to make are going to be directly proportional to the amount of error I have. In PI, I am going to have two terms. One is manipulated variable value is proportional to the error I have, and the other term is it is also going to be a cumulative effect. I am going to have a term corresponding to an integration of all the errors that I have had till now. So the first one is just based on present, the second term is based on the past. And if you extend this idea, you could come up with PID controller where the first term is based on the present P, the second term is based on past, and the third term is based on future because I am going to take the derivative, the rate at which the error is changing, which will give me an idea of how things are likely to change in the future. Then the PID controller in this time domain, I showed how they get translated into the Laplace domain, and the general controller structure is Kc times 1 plus 1 over tau is plus tau ds, which is a standard PID structure. Now you put the standard PID structure into your equation, y is some transfer function times YSP plus some transfer function times d, then you get the effect of set point and disturbance on y, and to do analysis you do the same things that you have done in open loop. So that is the first part of it, and then we saw how to analyze this, what are the advantages and disadvantages of these controllers through simple final value theorem. I showed that if you have a P controller, you will always have an offset. However, I also showed for some simple examples how the P controller is quite fast and changes the closed loop time constant or reduces the closed loop time constants very efficiently when compared to the open loop time constant. So P controllers are quick acting, easy to implement. The disadvantage is offset. The offset can be removed completely by including an integral action is what we showed again through final value theorem. So the advantages of a PI controller are that there is no offset, but we also showed that because of the integral action you can introduce oscillations. Now if you want to get rid of offset and minimize the effect of oscillations, then you go for PID controller. However, the disadvantage with the PID controller is because I have a differential of an error, if the sensors measuring your outputs are noisy, then your controller will chatter a little bit. Of course, one way to avoid that is to smooth measurement, but if you smooth the measurement, then the effect of future actually gets lost a little bit in that process. So conceptually PID, while it sounds great, in real implementation there are issues with some of these. So unless there is a very special need, there is a very specific case where you use this, typically PID is not used as much. PI is the controller that's used most, and P controllers are used in cases where you want fast control but you do not really worry about the minor offset that you have. So that summarizes PID portion of this course. Then we ask this question, okay, once we choose whether we are going to use P, PI or PID, how do we actually find the values for this k, c, tau I and tau d. Then I said before we do that, because this partial fraction idea is not going to be enough for us to understand this, I introduced the notion of Routh table. So here I said if I have a denominator polynomial which has coefficients which are all constants, then you can actually get the root resolve form and then understand stability. However, if I have these coefficients also as functions of the controller parameters, then we want to know what happens to the stability of the system, and without knowing the controller parameter we cannot actually get the roots and so on. Okay. So we came up with this Routh stability table where remarkably you can actually make decisions about whether there are any roots on the right half plane without ever computing the roots. Okay. So that is the beauty of this Routh table, and this table is needed because now I have coefficients which are functions of the controller parameters. So I showed you that if you have a polynomial, if all the coefficients are positive, then you go to the next step. If you have even a single coefficient which is negative, then we know there is at least one root on the RHP. So there itself we can stop and say there is a problem. But if all the coefficients are positive, then there is hope that there is no root in the RHP. So to further verify it, what you do is you construct this table, and if the first column of the table has all positive numbers, then we are guaranteed that there are no roots in the RHP. Again, the beauty is we are not actually computing the roots at any time. However, if there are some negative numbers, depending on the number of sign changes, you can figure out how many roots are in RHP. So the number of roots in RHP is equal to the number of sign changes that you see in the first column. Okay, so this is the Routh table. Then the next lecture we showed that how this Routh table is useful, because we looked at stability as being the tuning of controllers being done in two different ways. One way is through stability notion, the other is through direct performance based tuning. In the stability notion, we want to see how far we can push the controller, get the values and then back off. To figure out how far we can push the controller, we can use the Routh table. In the direct synthesis or performance based approach, we do not worry about how far we can push the controller. Instead, we say we know the closed loop transfer function, so let me directly give a transfer function for that closed loop transfer function and then back out the controller. The advantage here is since you are specifying the desired closed loop behavior, you can keep it stable, so you do not have to worry about stability. The disadvantage conceptually is you really do not know how much you can purchase out of the system. You are just doing something based on your understanding of how much you can get. The other issue with direct synthesis is if you are really looking at only PID controllers, because I am computing a transfer function for the controller, it need not fall in the PID structure. However, by choosing the G desired properly, I showed you that you can get to the PID structure. And in cases where you do not get to the PID structure, there are some things you can do where you collect the other terms and then generate what is called a filter function. So your controller becomes a filter times the standard PID structure. And then I said you do not have to panic because I have this extra filter, because the closed loop is simply GMC by 1 plus GMC, and C can be any form really. You can do the same kinds of analysis that you have been doing. I also mentioned that these are very important for you to understand fundamentally how all of these operate, but if you are a practitioner and then you are looking at implementing control, then basically there are these tables, there are these tuning tables, IMC based tables, tuning tables which are other types of tables. So all of these tables will give you the PID parameters in terms of either the process transfer function directly, or if in case of IMC tables you have to have the process transfer function and a G desired form, and the parameters in these will be used to compute the tuning constants in the PID controller. Okay. So with this the basic control part of this course is done. The next part I will start with this direct synthesis and then explain how we are going to look at more complicated dynamics which we have not seen till now. The first dynamics that I am going to talk about is what is called inverse response systems, and then I am going to follow it with the time delay systems, which will introduce difficulties which will force us to move out of this very simple numerator denominator polynomial form. It is going to introduce some more complications that need to be addressed. Then we will also look at unstable systems, and then we will look at truly multivariable systems in the next 1/4 of the course. So I will see you back again for that portion of the course. Thank you.